Hi everyone, this video is created for education purpose only. We are studying our S.Y.P-II Mathematics paper 2nd numerical methods and its application. We have already started our unit number 4 numerical solution of first order ordinary differential equation. Now in this video we are going to see third method for solving first order ordinary differential equation. That method is Euler's method of successive approximation. This method is developed by the great mathematician Euler. Let us see this method. So for that we should consider first order ordinary differential equation. Dy by dx is equal to f of xy with initial condition y at x0 is y0. You may call this as equation 1. So to find solution of this equation 1 at point xr, which is given by x0 plus rh, r is equal to 1, 2, 3. That is, if you put r is equal to 1, so you will get x1 is x0 plus h, r is equal to 2, x2 will be x0 plus 2h, r equal to 3, x3 will be x0 plus 3h, etc. Let us consider the interval x0 to x1. So integrate equation 1 in the interval x0 to x1. So integrate within the limit x0 to x1. So in the LHS integration x0 to x1. So derivative integral will get cancelled dy. The dy and then equal to integration x0 to x1 f of xy dx. In the LHS integration is y within the limit x0 to x1. So upper limit is x1. So y at x1 is your y1 and y at x0 is your y0. So in the LHS you will get y0 minus y1 is equal to integration x0 to x1 f of xy dx. So you will get y1 is y0 plus integration x0 to x1 f of xy dx. Now in the interval x0 to x1, so let us assume that this f of xy is nothing but f at x0, y0. So which is free from x, so that will come outside of this integration, and then equation 2 becomes in the LHS y0, y1 is equal to y0 plus, now f at x0, y0 as it is, and the integration of dx within the limit x0 to x1. So you will get this is x1 minus x0, and that is nothing but your h. So you will get y1 is y0 plus h f at x0, y0. Then similarly in the interval x1 to x2, put f of xy is f at x1, y1. So you will get y2 is y1 plus h f at x1, y1. Continuing this way, we get general formula. Yn will become yn minus 1 plus h f at xn minus 1 comma yn minus 1, or you can write n plus 1th approximation yn plus 1 is yn plus h f at xn yn. N is equal to 0, 1, 2, 3, etc. And this formula is called Euler's formula for successive approximation. So remember this formula, yn plus 1 is yn plus h f at xn yn. Now we will see examples based on Euler's method of successive approximation. So using Euler's method, solve the differential equation dy by dx is equal to 1 plus y square with initial condition is y at 0 is 1. Obtain y at 0.05, y at 0.1 and y at 0.15 by taking h equal to 0.05. So you have given h is 0.05. So let us see solution. Your given differential equation is this with initial condition y at x0. So y at x0 means y at 0 is 1. So your x0 is 0 and y0 is 1. Again, your f of xy is 1 plus y square. So f of xy is 1 plus y square. Then h is also given 0.05. So and your xr is x0 plus RH are equal to 1, 2, 3. So your x naught is 0, then 0 plus h u is your x1, so 0 plus 0.05, so that will be your x1, then x2 is 0.1 and x3 is 0.15. Now we will find value of y at these three xi's. So let yi is y at xi, means y1 is y at x1, y2 is y at x2, y3 is y at x3, etc. To find y at x1, that is y1, y at x2, that is y2, and y at x3 is y3. So the general formula for Euler's successive approximation is, what is that? It is yn plus 1 is yn plus h f at xn yn, n equal to 0, 1, 2, 3, etc. So put n equal to 0. So in the LHS you will get y1 is equal to y naught plus h f at x naught y naught. Now here we have to find f at x naught y naught, as x naught is 0, y naught is 1, and f of xy is 1 plus y square. So you will get f at x naught y naught is f at x is 0, y naught is 1, so f at 0 comma 1. So x equal to 0, y equal to 1, so you will get 1 plus 1 raised to 1, and that is 2. So here y1 you will get 1 plus h is 0.05, and f at x naught y naught we have obtained is 2. To simplify this, you will get y1 is 1.1, but y1 is y at 0.05, and that is equal to 1.1. Similarly, we have to find y2. y2 is, formula for y2 is y1 plus h at f h into f at x1 y1. Now y1 x1 is 0.1. Now y1 is 1.1. So we have to find f at x1 y1. So f at x1 y1 is f at 0.1 comma 1.1. So wherever x is there, replace by 0.1, and wherever y is there, we have to replace by 1.1. So f of xy is 1 plus y square. So put y is equal to 1.1. So that will give you 1 plus 1.1 bracket square, and that is 2.21, which is your f at x1 y1. So in this formula, put y1 is 1.1, h is 0.05, and f of x1 y1 is 2.21. So you will get y2 is this, and this is 1.2105. Thus y2 is nothing but y at x2. x2 is 0.1. So y at 0.1 is, this is 1.2105. Now to find y at 0.5, so that is your y at x3. Again formula is y3 is y2 plus h f at x2 y2. Now here x2 is 0.15 and y2 is 1.2105. So here we have to find f at x2 y2, as we have done. F of xy is 1 plus y square. Just replace y by y2. So you will get, it is 2.4653. So put f at x2 y2 is here. Then h is 0.05 and y2 is 1.2105. So you will get y3 is 1.2105 plus 0.05 into f at x2 y2 is 2.4653. Simplify this, you will get y3 is 1.3338. So this is nothing but y at 0.15, and that is nothing but y3, and value is 1.338. So here we have obtained y at different xi's. So this is very simple method. So just remember this formula. Yn plus 1 is yn plus h f at xn yn. So this is the Euler's method of successive approximation. Why successive approximation? It's called because wherever if you get y3, then to obtain y4 you have to use y3, then to obtain y5 you have to use y4, etc. Means to obtain yn plus 1, so you have to use nth approximation, that is yn. Now these are the exercises based on Euler's method. So this is dy by dx is equal to x square plus y. Initial condition is given, y at 0 is 0 and h is 0.01 and we have to obtain y at 0.02. Another example, dy by dx is x into y and you have to obtain y at 0.4. You have given h is 0.1 or 0.10, doesn't matter. 0.04 means 0.040. So obtain as we have done in the previous example. And then third example is again similarly, only change is in f of xy and wherever h is there you have to take care of that. In the last example h is 0.2 and you have to obtain 0.4, y at 0.4 and y at 0.6. So this is again a very easy method for solving first order ordinary differential equations. So this is about Euler's method of successive approximation. In the next lecture, we will see another method, that is Euler's modified method for successive approximation. Let us stop here.